Okay, we're going to begin our Chapter 18 study on direct current circuits. Let's bring up the PowerPoint, and here we go. We rely on circuits for all kinds of modern conveniences, such as electric lights, electric stovetops and ovens, washing machines, and lots of other appliances and tools. Electric circuits are also found in our cars and in all types of medical equipment. For this topic, we will analyze simple direct current circuits which includes resistors or capacitors or both. Our analysis will be simplified by using two rules known as Kirchoff's rules, which follow from the principle of conservation of energy and the law of conservation of charge. Most of the circuits are assumed to be in steady state, which means that the currents are constant in magnitude and direction. For the circuits containing capacitors, the current will vary with time. Now, why are they showing birds on a wire? That wire actually has high voltage on it, but because they're at the same potential, they're not harmed at all. If somehow they were able to touch ground and the wire, they would be fried. But we hope that doesn't happen to the birds. All right. Now, let's take a look at the figure on the left. The battery is a source of EMF, and it contains the current in the circuit. And it maintains this current in the circuit, I apologize. An EMF source is any device, such as a battery or generator, that increases the potential energy of the circulating charges. We can think of an EMF source as a charge pump that forces electrons to move in a direction opposite the electrostatic field inside the source. The EMF of a source is the work done per unit charge. So the SI unit of EMF is the volt. The figure on the right is the schematic of the battery and resistor circuit. We can assume the connecting wires have no resistance. If we neglect the internal resistance of the battery, the potential drop across the battery, the terminal voltage, equals the EMF of the battery. Because a real battery always has some internal resistance, the terminal voltage is not equal to the EMF. In the diagram, the battery represented by the dash rectangle consists of a source of EMF in series with an internal resistance little r. Let's imagine a positive charge moving through the battery from A to B. As the charge passes from the negative to the positive terminal of the battery, the potential of the charge increases by epsilon. The charge moves through the resistance R. Its potential decreases by the amount IR, where I is the current in the circuit. The terminal voltage of the battery, delta V, is the difference in the potential between points B and A. So we can write it as shown here. Delta V equals epsilon minus IR. You can see that epsilon is equal to the terminal voltage when the current is zero, called the open circuit voltage. Take a look at the schematic. We see that delta V also equals the potential difference across the external resistance R, which is often called the load resistance. Combining these relationships, we get this. Delta V equals IR, which converts to epsilon equals IR plus I little r, the R being the big resistor and the R being the internal resistance. I equals epsilon divided by R plus little r. From this result, you can see that the current in this simple circuit depends on both the resistance external to the battery and the internal resistance of the battery. If R is much greater than little r, we can neglect little r in our analysis, which we usually do. We did it in the experiment that we conducted Thursday. Let's multiply the E equation by current. So we multiply both sides of that middle equation, multiply by R. IE equals I squared R plus I squared little r. Okay, from this equation, you can see that the total power output of the source EMF is converted at the rate at which energy is delivered to the load resistance plus the rate at which energy is delivered to the internal resistance. If the internal resistance is much less than the load resistance, then most of the power delivered by the battery is transferred to the load resistance. In general, unless otherwise stated, we will assume the internal resistance of a battery in a circuit is negligible. It's just important to know that it is there. This ends this section. The next section will be section 18.2, resistors in series.